this is my selector. My selector will be only 1 bit. Okay. The number here, why is it 2? Because it is taken as 2 to power of the number of selector. So I put S here. So if selector is 1, input will be only 2. So all multiplexer, 1 output only. So if the number of selector here increase from 1 to 2, then you find that because here S become 2 already, then 2 to the power of 2 give you the 4 inputs. Increase further to 3 bit, then you find that 1, 2, 3, 2 to the power of 3 will give you the 8. Okay, I should have 8. So 0 to 7. So 8 bits. But my output still only 1 bit. Multiplexer, we can name them as, say, for example, in this case here, we call them 8 to 1, okay, line multiplexer. Sometimes we skip this word here, line, okay. We just name it as 8 to 1 multiplexer, okay, multiplexer. Or instead of write in this form, I also can write as in this form, okay, just like that, okay, 8 to 1. Always this is the input and this is the output. All right, so multiplexer function this way. I have all my input. I can put in all my input over here. Then this input, okay, will becomes the output. And which is the input that becomes the output depends on selector. Okay, depends on selector. Selector is the one that decide which input to, okay, place at the output here. Therefore, multiplexer have the name here called data selector. They select the data to becomes the output. All right, so this is everything that I mentioned just now. Okay, now in this case here, you are going to find that, okay, some multiplexer here, they have an extra control input, your enable, or they call it as stroke. Okay, lines to provide, okay, greater flexibility. So if you have an enable input here, in this case here, okay, although I have input, okay, I have input over here, but if I make it disable, means that, okay, this enable input here, I make it not functioning, then you're going to find that although, okay, I change my input combinations at the selector, my output, okay, I still don't get what I want because I will disable the input. So to have this one here, you find that you can have a greater flexibility. You can design it, okay, as no multiplexer trees and so on. Okay, so you only want, okay, one multiplexer in the circuit. So in your circuit here, there are many multiplexer. Let's say you only want one of them to function, then you can play around with this enable. All right, so common name more on the enable. So look at this simple, okay, 2n to 1. Like I say, the n here refer to my selector input, selector input. 2n to 1 line multiplexer symbol. So look something like this. And okay, now how does the output lines here looks like? Let's say my output here is the F, and we make this multiplexer here more simple. Only 2 input. Otherwise, okay, my equation will be very long. Okay, we make it only 2 input. My S, okay, is S0 and S1 only 2 input. Therefore, 2 selector input. Therefore, my input here, of course, I have I0. This is I, okay, I0, I1 up to my I3, okay. Let's take this one here as my I3. So 4 input lines, 4 input lines. Okay, so my output here depends on selector condition and the data input conditions. Of course, I must, okay, make sure I enable this multiplexer. So enable in this case here, let's say you see the enable, okay, is connected as in this form. That is to say that to make this multiplexer here working, to make it work, my enable must be connected to a logic 1. All right. connected to a logic 1. Then, if this is 0, 0, okay, if this is 0, 0 conditions that I set, you are going to find that my output, okay, will show me the conditions of I0. Okay, you will find that, okay, my output will show me these conditions. Next, if I change my selector input to 0, 1, then whatever is the condition, whether logic 0 or logic 1 input at this I1 will appear at my output F here. Subsequently, change again for my selector input, then you find that the I2 conditions will appear at the output, and lastly, this one here, they will pick I3. So this is a simplified truth table for my 4-to-1 multiplexer. Of course, okay, if I want to add in the enable, I put in the E here, and I tell you E always 1. If my E is 0, okay, I put it at the last here. If my E here is a 0, sorry, okay, right, too big already. So whatever is the conditions here, okay, you are going to find out your F here not functioning. They only show you a 0 output. So this is a part here. I keep on changing here. Although I have 1 here, you just find that your output, no, not going to show you anything. Why? Because your enable is a 0 in this case. So enable in this case here 0, we say disable the chips already. Disable. Make it not working. Okay? Disable the chips already, or disable this multiplexer. All right. Therefore, my F here, okay, the function, okay, output functions here is given by these expressions. When my selector both are at 0, 0 at the time, okay, they pick I0. Or when selector is a 0, 1, they pick I1. Or this condition, they pick I2. This condition, they pick I3, provided my E is a 1. All right, so this is a output equation for a simple 4-to-1 multiplexer with an active high enable. So if we say that, okay, it responds to a 1, then we say that it is a active high enable. All right, so if you see here with a bubble, a small circle, we read it as bubble, okay, then we call this one here as a active low. So to make this multiplexer here work, I must put a 0 to it, okay, active low. Okay, so to make it work, I must put a 0 to it. Therefore, in this case here, we don't remember how to make a multiplexer here work. We have to see the data sheet. Okay, check, enable, how to make it work. Should I put a 0 or should I put a 1? Okay, look at the symbol. All right, look at the descriptions. Okay, if the symbol is not clear. All right. Okay, so truth table can be start off with something very complex. All right, in this case here, and you see I0, 2 or I0 here. When these conditions here, I0, all right, but input combination remain unchanged. So we are actually, okay, just now the truth table that I show you here is actually, I already combined the two together. All right, I combine the two together to make it, okay, a more simplified version. Okay, this one here is a simplified version. So if I want to use a VHDL to write, okay, to write a multiplexer, I will use this version rather than this one here. So although this is a more complete version. All right, so remember the earlier one, okay, is easier. But okay, this part here and the earlier version, both okay, you find that okay can be used to see the internal architecture of your 4-to-1 multiplexer. So my equations, as I mentioned just now, is given by this one. All right. So how to build this circuits here in terms of hardware? So I must build, okay, an output which is n together, this function, another output n together, third and fourth, okay, both are N together. So this one here, so look at it, this one here, my I0, okay, this is I0, this both are bar, right? So S1 bar, S0 bar, I end them together, okay, I end them together, okay, and in this case here, I must make sure my enable working is E is a 1, okay, I put a 1 here. So same thing, the second one come from here, third come from here, fourth come from here. So this all here tells me that I all them together. Okay, look at this internal architecture here. Imagine, okay, if E here, I put a 0 to it. I input a 0 to it. Then you are going to find that this input is a 0 for all the AND gate. All their enable will be 0. So you know this is the AND gate. When input is a 0, automatically, okay, your output will be 0. So therefore, we say that, okay, no matter what is the value that you put here, sorry lah, my output here, I'm only going to see this 0. So to make it work properly, please, in this case here, it must be a 1. Then with this 1 here, I just need to check these 3 inputs. Okay, is my selector correct? 0, 0. Let's say connect collector, selector, I put 0, 0. Go through this inverter, become 1. Become 1. Then all this now enable is a 1. These two also 1. What is the output here? Depends on my I0. Okay, depends on my I0. Whereas in other combinations here, you are going to find that, okay, you are going to find that, okay, let me clear this one here first. Okay, this one here is also a 1. All other combinations here, either one of these are 0. Okay. So although this one here give you a 1, but the S0 is going to give you a 0. All right. This part here, my S1 is going to give me a 0. This one here, both of them are going to give me 0. So for AND gate, the moment we see one of the input is a 0, output will be 0. So with this, okay, you are going to find that my outputs here, okay, my outputs here depends on I0. If selector is 0 for S1 and also 0 for S2. Okay, same explanation can be given for the rest of the outputs here. All right, so it depends on the selector that is going to select which input is to be the output. So this is the internal structure of it. Don't need to remember this structure. What you need to remember is the equation, because based on this equation, I can draw this circuit. All right, next. So you are going to find out, okay, in a market, okay, if I were to tell you, I want to build a 4-to-1 multiplexer, very easy. I go and buy 8-to-1, no problem, can buy also. All right, 16-to-1, maybe still can get. What about 32-to-1? Maybe still can, but what about 64? Then you find that, maybe cannot find this component. All right, but I got 64 input. So what am I going to do with it? So what we can do is we can build a multiplexer 3. So in my this example here, I am not building a 64-to-1 multiplexer, but instead, okay, I show you how am I going to build, okay, 16-to-1 from 4-to-1 multiplexer. Same concept can be used, because this one here too big. All right, too big. Too big in the sense that, okay, the way we draw it is very difficult. All right, or otherwise, okay, very small. All right, so I show you, okay, is making use of 4-to-1 to build 16-to-1 multiplexer. All right, so you find that here tells you commonly commercially available, can buy easily up to 16-to-1. All right. So you can do interconnections using several multiplexers in a tree-like structure. Build it like a tree here. Then you can produce a larger multiplexer. So example, five. This is 5 unit 5 unit of 4:1 can build you 16:1. 5 16:1 then can form you 64:1. So I show you this one. If you want to build 64, you make use of this concept. So replace the 4:1 multiplexer with 16:1 multiplexer. All right. So you find that now. My multiplexer here is 16 input. All right. But I don't have a 16 input, okay, multiplexer, but I have a lot of 4:1 multiplexer. So what am I going to do here is I use 5 of them, okay? So this is my first level, all right, first level. This is my second level. My this multiplexer here, okay, they are input selector, the selector, because it's 16 ma. So selector, okay, in this case here, is connected to your X3, X2, X1, X0, 4 input. So these are the selector input. Okay, selector input. Okay, these 4 combination. And you are going to find that, okay, what I do is I make use of this one, the most significant 2. I connect it here. The rest, X1 and X0, I connect it to the first level, all same. All right, all I connect to here. Then they are input now. So you know that the data input now because there are 16 of them. Okay, so it will be from I0 up to your I15, 16 input. So you are going to find that it is from here. So this one here give me the first 4. Okay, followed by I4. This is I4 to 7. Okay, 8 to 11, 12 to your 15. And output from this first level multiplexer here, I make it becomes the inputs here. Okay, second one, third, and fourth here. Let's say now, okay, we test out, okay, whether are we doing the right thing. So let's say now, okay, I give you a combinations of I simply choose 1 0 1 0. My selector input for this 4, I put in as 1 0 1 0. That means that here is 1 0, right? All these also 1 0. Okay, all these also 1 0 because of these 2 are 1 0. Then here will pick you the I2. Here pick you the I6. Here I10. Then here I14. Okay, but my output here by right, okay, when I look at these combinations here, what I should have is I10. Okay, remember 1 2 4 8. So 8 plus 2 give you the 10. All right, 10. So my output that I'm supposed to show here actually is the same as X3, X2 bar, X1, X0 bar, I10. Okay, the output for this one is this one. So since this one has been fulfilled, okay, because of the selections here, now I10 will be the output. Now, although, okay, I2, I6, I14 are waiting here, but because I2, these are X3 and X2 here, the selection is 1 0. So I10 1 0 1 0. So see the 1 0 here. So I10 will become the output. So that is to say that, okay, I can actually make use of 5 5 unit of 4-to-1 multiplexer to form, okay, the 16-to-1 multiplexer. All right. So of course, okay, if you want to make it larger, you just replace this one with larger size of multiplexer. And if you replace it with larger size of multiplexers here, maybe there are some pins that you don't use. For example, okay. Okay, for example, let's say now, okay, I want to have, okay, 64-to-1. So from 16 to 1, okay, multiplexer. Then you find that this one here, I use 16-to-1. So because it's 16-to-1, so 1, 2, 3, 4. I need 4 inputs. All right. Then every one of these same size, so you find that you have 4 input. 1, 2, 3, 4. Okay. 1, 2, 3, 4. And this one here also your 1, 2, 3, 4. Now, here 16, another 16 input. Okay, every one of this one here, 16 input. All right, 16. So your 16 times your 4 is going to give you the 64 input. All right, so these are all the I0 up to the last one here, I3. So what I do here is the I0, here I16, right? By right, sorry, I15. Okay, I16. This one here, 63, I63, because 64 input start from 0. So you find that this output go to first one. This output go to the second one. This one go to the third one. This one go to the fourth one, go to your I3 only. Then what about the rest, the I4 up to the I15? What you can do is, because these are the extra input pin you are not using, okay? You don't leave it hanging. You short it to ground. We make this input here become 0. And therefore, my outputs here, for this part here, I need to do, because 64, 2 to power of this 6. 5 is 32, yeah, 6 only. 2 to power of 6 is going to give you 64. So therefore, you find that these 2 pin, okay, you can put in anything. Don't care lah. What I mean, either a 0 or 1. But this 2 pin, okay, is the one that decide which one, okay, will be selected, becomes the output. Because by right, 64 input, I require only, okay, 6 pin. But here, now I got extra pin already. That is to say that you can actually further expand it, you see. Instead of 64, you can make it as a double of this one, 128. Make use of this pin. Okay, I4 or even 256. Okay, one extra pin, the pin 5, I5. Okay, this one here a bit blur. So 52, 512. All right, more pins. Okay, so that is to say that there's no need for you to stop at 64. If you want to make it larger, now this structure is still okay. So if that is the case here, please, this is not don't care. You must make sure you fix a values to it. All right. So if you're afraid that, okay, this part here, you simply put don't care here, it's going to disturb or jumble up your design. What you can do is, okay, those whichever you are not using one, okay, you short it to ground. Okay, short it to ground. These two you short it to ground. So this is input, you can do it, but output never ever we go and short it to ground one. Input we short it to ground to indicate that we are not using this one. So if you want to use it, okay, you disconnect this one, connect to whatever input conditions that you need. All right, so this is how we can expand, make our multiplexer here become larger. All right, any questions? If there's any question, okay, can ask here. All right. So next, okay, we look at a little bit of multiplexer application, and you're going to find that my tutorial, okay, mainly, okay, is on these multiplexer applications. All right, so you're going to find that multiplexer, we can use it for transmissions of informations, okay, from several sources over a single path. That is actually the main thing of multiplexer. Okay, try to recall this example that I think I mentioned before when you are in year 1. I say, okay, in the computer lab, okay, or computer center, okay, in the computer center, normally, okay, you are going to see this, a lot of these are computer, okay, computer A, computer B, C, just I take example, 4 unit, can have more, so a big computer lab, and all these computers, computer terminal, right, or CPU, their output, okay, one of the output, okay, you are going to make them connect to a multiplexer, okay, and this multiplexer's output only one, okay, this is a 4-to-1 multiplexer, for example, is going to be connected to a printer. Because in most of the case here, we do a lot of processing, okay, in the computer, and finally or eventually we send it for printing, and printing can be very fast. So there's no need, okay, to have one computer connect to one printer. So if you need to print, you send a print request, okay, to your multiplexer, maybe send a 1 here. If you are not sending anything for printing, so the input coming in to multiplexer is 0. Okay, so there are selector here. Selector keep on, okay, rotate lah. They keep on scan, okay. Remember something like a ring counter, things like that, okay, they keep on rotating. Oh, now they saw a 1 here, come from A. So what is the A condition? 1. Okay, 1 means that my printer going to print. Okay, so once sent already, these multiplexers are selected, continue, okay, the rotation work, they go to B. Oh, B0, okay, nothing I need to do. Okay, C send a request here. So make a C as the output, Q here, waiting here. Once A complete the printing, C will continue the printing. Okay, so a very common and application and can be understood by everybody lah. Okay, in these parts here. Here they say provide for the transmissions of information from several sources. My ABCD are my sources over a single path. Okay, this is the single path. So you are also going to find that, okay, a multiplexer can also be used together, okay, in conjunction together with a demultiplexers for connecting information from several source location to several destination location. It's like that. Okay, just again, example is only 4 input. This wire very long one, from Kuala Lumpur, okay, maybe connect to Johor Bahru or connect to Penang. All right. So you find that, okay, this is my multiplexer used together with a demultiplexer. Demultiplexer having a structure terbalik, okay, compared to multiplexer. So demultiplexer, 1 input. Example here, 4 outputs. Demultiplexer also have selector. All right, and they will be synchronized, these two. So I have 4 different input. Want to go to places W, X, Y, Z, for example. So you see, okay, when you are trying to pass your info the time, you can always do time multiplexing. Package by package, you send the informations. which you are going to study under communications. All right. So if I here indicating 0, 0, A will be passed on to here, followed by 0, 1, B will be continue. So A information first, then B information, C information, D information. Okay, are going to be convert or sent to these 4 different destinations in this case. Now, depends on the selectors over here. Where do you want A to go to? So when A is here that time, depends on your selector's conditions. So of course, these two, you have to know, program correctly, synchronize it properly. So if A, you want it to go to W, make sure you synchronize here, start off with 0, 0. Then followed by B, if you want to go to Z. So from 0, 0, Z, so you go to 1, 1. Okay, at the selector here. So then B will go to Z. C will go to, say, for example, your Y, which is 1, 0, and D, let's say, go to X of 0, 1. So the synchronization part of your selector is very important. Otherwise, okay, you will be sending information to the wrong place. If it's confidential, then habis lah. All right. So this is what is being meant by this one, and I used very commonly in those fixed line telephone. Okay, if at home, okay, you still have a fixed line telephone, they are going for this type of concept. Because the cable here, okay, we cannot be laying, okay, too many cable, very expensive. So they lay one cable, they go to, okay, in a Penang, there are a lot of user, right? So which user they, set up lah. All right, so they can form, okay, the multiplexer tree, they can form multiplexer trees here so that, okay, many inputs can come in. Okay, so these are the general applications of your multiplexer. This is in conjunction together with your demultiplexers over here. Okay, other than this, okay, you'll find that, okay, multiplexers here can be used, okay, to produce, okay, any circuits, okay. So this part here is what I already mentioned just now, all right, what I mentioned just now, the multiplexing example. Okay, look at this part here. The drawing is nicer. All right, destination address, suka hati, where do you want to go? Make sure synchronize properly, Okay, next, okay, is on the logic design, okay, here with your multiplexer. You're going to find that, okay, your output for multiplexers here is given by this one. And this equation here is for a 3 selector line. Okay, my 3 selector line, in this case here, my X3 is connected to X2 is connected to X, S1 connected to Y, S0 connected to my Z. Okay, not every time we will use S, we can use any label and any label here that connect to these points here. Now, those label that I connect to this point here, I call it X. Okay, Y and Z. All right, and this is the data input. FO, F1, and so on. So this is the general equations, okay, or the Boolean expression before we do any simplifications, okay, for a 3 input selector line of a multiplexer. So if I want to do logic design with these multiplexers here, you find that, okay, let's say we start off with something very simple. These are my 3 input variables. So 2 to power of 3, recall, for truth table here, I must have 8 combinations. All right. So this one here, hope you still remember. Actually, it's the min term 0, min term 1, up to my min term 7. Min term in this case here means that it's a X bar, Y bar, Z bar. And or it's a product. Okay, N together one. But as for this one, this is a 1 so it's a X bar, Y bar, your Z. All right, so we write according to this. So for this case here, M3 given as in the case of min term, X bar, Y, Z. All right, and so on. So this is what we call min term. Now you are going to find that I can design this truth table here, okay, or this table here, actually based on the Kano map, based on Boolean algebra, or easier one is using multiplexer. But of course, okay, slightly more expensive lah, because multiplexer is much more expensive as compared to a single chip, okay, those AND gate and OR gate. But very simple design. So what you do here is, this is the input, right? You are going to make it connect to your selector S0, S1, and S2, S1, and S0. When you write your truth table as in this form, usually, okay, you will take this one here as our MSB. This is the LSB connections. So go to the highest one is 2, the lowest one is the S0 in this case. And for these multiplexers here, very easy, okay? They have all the combinations that I want. When these are 0, 0, yeah, this is the 1. So pick FO lah. So whatever is the conditions here, connect to here. Whatever is the connections here, connect to here. And so on. All right. And in order to make this multiplexer here work, in this case, my E enable, no bubble, connect it to a logic 1. Otherwise, you won't be able to get your output. All right, so you find that, okay, my multiplexer can be used, okay, to implement logic function. This is what we call logic function. My multiplexer is being used, okay, to implement logic functions. Build a circuit. All right, so this one here very simple because, okay, 3 inputs. My size of multiplexer big enough, okay, got 8 inputs. 3 input, I need 8 combinations. 8 input here covers all the combinations already. So directly just take whatever is the output. But in some cases, you're going to find that, okay, what happens, okay, I don't have a 8-to-1 multiplexer. Then I may need to use a smaller size of multiplexer. Let's say 4-to-1. All right, things like that. So in that case here, how am I going to do it? Now here, they ask you to consider this min-term, okay, min-term. And min-term canonical form. Hope you still remember. Canonical form means that before I go through any, okay, Boolean algebra or any simplifications, so it contains all variables. Okay, contains all input variables in the product terms. Then you call it, okay, canonical form, product terms. Okay, let's say, for example, here, X, Y, Z, X, Y, Z. So these are the one that we call it as input variables. Okay, 0. A min-term canonical form means in this case here is X bar, Y bar, Z bar. 5, okay, 5 is 4 plus 1, right? X, Y bar, Z. So you see, I show you just 2 lah. So you find that, okay, these are terms here contain all the input variables. Okay, there's no such thing as XY only or XZ only. So when you use the word canonical, means that all, it contain all input variables. Canonical. So looking at these formulas here, actually, okay, my F here, instead of writing it in this form, you can also write it as in this form. Summation, you sum them together, so I all it. This is the one that X2, so 2, right? So this one here, 3, right? Okay, and the last one here is 5. 1, 1, 4. This is a 1, 2. Okay, this is a 2. Yep, this is 0. Okay, so my function can be written as in this form. But of course, this one here more tedious, right? So therefore, we write in this form, which we will cover in the year 1. All right, then you find out now if you are familiar already, you can actually skip these steps. If not now, okay, try to recall. How am I going to build my truth table for this particular functions here? Because of 0, 2, 3, 5, you find that this is a min term 0. M stand for min term. Okay, M here stand for min term. Small letter M. Okay, min term 0, min term 0, 1, this is 2, this is min term 3, min term 5. Okay, so whatever as functions given here indicate to you this, their output is a 1. Okay, so I put in the 1. All right, whatever not mentioned here, their output is a 0. So we put in 0. So you'll find that for me to implement this truth table here or these functions here, very easy. I use a single multiplexer, 8 to 1. Okay, 8 to 1. I take whatever is the input. Okay, connect to whatever is the conditions that I want and finish my design. Okay, I finish my design. So this is provided my input. Okay, my input pin here can cover all these output functions. Then my design can be very simple. All right, and now here, continue here is, like I mentioned earlier, unfortunately, okay, I don't have a 8 to 1 multiplexer, but I have several numbers of 4 to 1 multiplexer. Then I am going to use a design based on 4 to 1 multiplexer. All right, of course, these are things here, you can extend it to a larger input. Let's say here input is a 6 input. Then okay, I can, instead of 6 input, you know that, okay, you don't have such a big size of multiplexer. Then you try to use a smaller size of multiplexer. All right, so this concept, okay, extend it this way. All right, so here I'm going to see is I'm going to use a 4 to 1 multiplexer to implement the XYZ earlier. Just now the min term is written as this form. I will show you how I got this. All right. Then you are going to find that I can factorize these expressions here. Actually, suka hati saya when I want to do factorization that time, should I choose XY or should I choose YZ? Nobody choose X and Z because very tedious. You are going to kill yourself only. All right, so we either choose XY or we choose XZ. Sorry, YZ. Okay, we choose YZ. So in this example here, I try to factorize it with these two terms. So you find out, okay, I tick up the X and Y. So X and Y, so bracket here is a Z bar. X and Y I took out. And you find that when I took out this X and Y here, actually these two, okay, these two, we can combine them. Okay, we can combine them. Last one, take out the XY, left with Z. Of course, okay, remember your Boolean algebra, this is equals to 1. All right, equals to 1. All right, now check my combinations of X and Y here. Both are 0. So both are 0. So 0, 0. This is a 0, 1. This is the 1, 0. So what is missing? X, Y is missing. So I add it in. So we add in this one on our own to cover all the combination. Add in on our own. Okay. So it covers 0, 0, 0, 1, 1, 0, and 1, 1. All right. And you are going to find that now if I connect my X and my Y to the selector, because here got only 2 selector input, therefore I have only 4 input. All right. And what to choose for this one depends on the value of the ZO. Z, okay? Z, okay? Where Z is a bar. First one. because this is 0, 0. So this one here forms my I0. My I0, I make it connect to my Z bar. 0, 1 that time, yeah, it's a constant 1. So easy, okay? I make it connect to a 1. 1, 0, okay? That forms my I2. This is I1. This is I3. So this one here, I make it connect to a Z. Whatever is the conditions of the Z, okay, this is the result that you're going to see here. Last, the I3 here, I make it shorter to ground because ground. And with this, okay, whatever is the input combinations of my XY here, they will pick this one to becomes the output. And you see the conditions at the output. So from this case here, you're going to find that so instead of using 8-to-1 multiplexer, now you are using 4-to-1 multiplexer. All right. So I will explain so you can sort of skip this one, directly see this. So you find that, okay, I reduce it, okay, I am going to make the connections of this form. And of course, okay, make your multiplexer here work, connect proper logic level to your enable. So this one here, this output F here, this output F here is exactly the same as this one. Okay, exactly the same as this one. But the size of the multiplexer that you are using here now, half. From 8-to-1, now you reduce it to 4-to-1. Okay, actually we can further reduce it to 2-to-1 if you want to. All right, so next, okay, we look at another example. Here we are trying to have a selector, it's a 4 variable. My truth table is a 4 input. Okay, it's a 4 variable Boolean function. And now, okay, instead of using 16-to-1 or 8-to-1, I want to use 4-to-1. I want to use 4-to-1 line multiplexer. Let's say this is the question. Okay, this is the function that I want to implement. 4 input, W, X, yeah, my mistake. Okay, W, X, Y, Z. All right, so these are the functions that I want to implement. So as mentioned, I need to make use, okay, of 4-to-1 multiplexer to implement it. All right, you find that 4-to-1, 2 selector line only. So in this case here, suka hati lah, which one you are going to choose. Either you choose WX or you choose YZ. Suka hati. In this case here, I choose WX. Okay, that is to say that my multiplexers here, 4-to-1, I choose my WX, connect to my selector input. And here, because of 2 input, I have I0 up to my I3 over here. My question now is, what should I put here? Okay, output is fixed, 1 line only. So we play around with these equations here. So you take out a common, okay, WX, okay, WX. Take out this first one. Now we take it out according to the order of when these two are 0, 0, followed by 0, 1, followed by 1, 0, followed by 1, 1. All right. So first, okay, take out these two here. They are 0, 0. Okay, 0, 0. And when I take out these two terms at time, you find that this one, okay, this one here, okay, and this one here, both of them, okay, having the same, okay, conditions of my WX. Both are 0, 0. Therefore, I can group them together. Okay, I group them together. Okay, next we proceed to 0, 1. Do I have a 0, 1 here? Do I have a 0, 1 here? No, right? So actually 0, 1 means that, okay, 0, 1, you add it in on your own because you don't see these expressions of 0, 1 here. So you are going to end them with a 0. No 0, 1, huh? Okay, so this is the 1, 0. 1, 0, again, not the same. So 1, 0 got only one term. All right, so you take out this 1, 0. Lastly, you take out the 1, 1. Okay, so move to this line here. These two remain unchanged, but this one I can simplify. Recall, so I simplify it by this way. Okay, so take out the common z bar. Then you have here is y bar. This is y. Y bar plus y equals to 1. Therefore, you don't see anymore. So left with only z bar. Okay, this is a term. And this is the one for my I0 because this is 0, 0. This is 1, 0. So it's my I2. This is 1, 1. Here forms my I3. Okay, I add in the I1 on my own, which is a 0. Therefore, in this case now, okay, I am going to connect Z bar to here. I'm going to connect the Y n with Z. Okay, I just write here Y n with Z instead of draw out the AND gate. I just write here first. Okay, and sorry, I make a mistake. The second one is a 0. Okay, second one I connect it to ground. Okay, because it's a 0. All right, third one I connect it to Y n with my Z. Fourth one, I connect it to Y bar and with my Z. Therefore, in this case here, okay, 16 combinations here, I can make use of 4 to 1 multiplexers to implement it with some simple logic gates. Either it's AND gate or sometimes you see OR gate, okay? It's either AND gate or OR gates only. Of course, okay, if you need to have a Y bar, for example, then an inverter lah. All right. Inverter is a must, okay? Although if you are not using 4 to 1, maybe you use 8 to 1 that time, okay? If it's a Z bar input, you also need to use inverter already, okay? They're not yet. All right, so this is trying to reduce these parts here. Then you find out, okay, this is the one that I'm going to see for my connections. So more practice, okay, we'll see during the tutorial. All right, okay, so multiplexer done. Any questions? Anyone with any questions? Macam okay, oh? Oh, yeah, loh, macam okay, So our test will be on start from multiplexer. Start from 5 input variables. 5 input variable, sure question come out one. Okay, 5 input variable is a sure questions. Of course, different input variable will be given. And normally, okay, seldom students get full mark for that part. Somehow they miss out something. Okay. Any question? If no question, we take a break. Okay, then we are going to continue. So I see you now. Okay, 9 minutes later. 11:15. Okay, any question before we continue a new topics on this adder? I hope to finish, okay, adder and comparator by today. Any questions? Okay, so I assume no. All right. Okay, we continue with this binary adder and subtractor. How we are going to add or subtract, okay, any binary number. Of course, okay, adder, as what we have studied in the year one, we know that adder, there are two types. One is half adder, the other one is full adder. Half adder consider only 2 bits, okay, but full adder consider 3 bits because they consider the carry in from the previous bit. So in our this part here, we focus on full adder. So they are performing, okay, additions at a single bit positions. And in the truth table here, you find this, okay. I have my this full adder, all right. This CI here stand for my carry in. X and Y are the 2 bits that I want to add up. I here means that, okay, say for example, okay, let's say I just put here as X, this is Y. So I have 2 bits, so X1, X0, Y also 2 bits, Y1, Y0. So I here means is either, in this example, either your 1 or your 0. So 0 will be added up with 0, 1 will be added up with 1 from the carry bits, okay. Now, so when we add up, okay, we are going to have our carry out and sum, all right. So taking for example, okay, just a recall. Let's say I have 0, 1. This is my X, X1, X0, 0, 1. And my Y here is 1, 1. All right. First, okay, when I add, okay, this LSB bit at time, of course, okay, there's no carry. Carry, okay, at this case here is a 0. So you can put in here as a 0. But subsequent bit here, actually, I don't know. I have to wait until I finish this addition. All right. So in this case here, you take 0, you add with 1, you add with 1 again, you are going to get here as 0. New, okay, carry out. This is carry out from previous addition. Now forms the carry in over here. All right, so I filled up this one over here. So with this one, we add up some 0 and 1 here. So imagine this is the same as a decimal 1. This is the same as decimal 3. So you add up, actually you get a decimal 4, right? 1, 2, 4. So this is how we do the addition. So in this table here, they only show you one of these, okay? All the possibility of all this, okay? When my C is a 1, when my C is a 0. So all the possibility. So you add up. So this one add up, all are 0. You add up these 3, you get 0, 1. So you have a single 1, you get 0, 1. When you have a double 1, you get 1, 0. Single 1, 0, 1. Double 1, 1, 0. Double 1, 1, 0. So if you have all the 3 inputs here are 1, then you are going to get your 1, 1. Your sum is a 1. Your carry out is also a 1. All right, so this is a table. And now let's say I want to do design based on this full adder. All right, based on this full adder here, you are going to find that, okay, I will design one C out and another one here, my sum here. So since this is 3 input, I am going to prepare Kano map. Okay, Kano map for it. And I filled up. I hope you all can remember Kano map. 0, 0, 0, 1, 1, 1, 1, 0. And this is 0, 1. All right, so we fill in according to the min terms. So this is the min term 0, min term 1 up to my min term 7 here. So this is always, okay, think about it, okay, how you are going to put your these variables here. So in this case here, this variable is put as a x. All right, suka hati ya, I put x. This part here, I put okay, y, c, y, c. All right, and with this, okay, the mean term is here. This is more significant, okay? So you are going to find that they move horizontally. So 0, 1, 2, 2, 3, 4, 5, 6, 7. So we fill up, okay? And this table, I want it to be for my sum. Okay, so we fill in 0, first one, second, 1. This one is here, okay? 0, 1, 2. All right, followed by 0. Next, 1, 0. This one, okay? And this 0 appear on this side. This one appear here. And we do the same thing for our next, okay, Kano map, which we prepare for carry out CI plus 1. So fill up 1, 2, 3, 0 first. Fourth here is a 1, then 0, 1, 1, 1. All right, and we do looping accordingly. And you are going to find that, okay, the sum outputs here, we can't loop them. But the pattern, okay, interesting, okay, always, okay, alternate. So if you see like this case here, you can sort of imagine that this is like a XOR gates already. So we confirm later. All right. This part here, we do this part here first, okay, easier. So you find that, okay, I have 4 ones over here. So although this one here, okay, they have been looped many times, 3 times, but all the loopings here are valid because, okay, in any of these loops here, there's a single one, which in this case, this one, as well as this one have not been looped earlier. So all these looping are valid. And if I write down, okay, these loopings here, you find that what I do this one here, the one constant, I write down the constant, x bar, okay, sorry, x, I, and my ci. Okay, first one. Next, for the vertical one, y, ci. Okay, sorry, I see the wrong one. Y, ci is the vertical one. This one here is the x, ci, this one. And this one here is the xy. All right, x and y here. All right, so should be no questions on this part. So I can make use of 1 AND gate, 2 AND gate, 3 AND gate, all them together to get my carry out. Okay, now we focus on the sum here. Sum expression, so since it cannot be simplified, so you find that their expression is written like in the canonical form. Contains all the variables, the x, y, and c. Every terms got 3 variables, x, y, and the c. All right, so move to here, exactly the same. So with this one here, you find that, okay, I am going to confirm to you that this is the XOR functions. So suka hati saya, okay, how I want to start. So in this example here, I take out the common C input. Okay, take out this common, then this part, copy this, C, okay, another C appear here. So copy down the XY. Next, consider these two, take out the common C bar. All right, so then we have this. Okay, this is for this one. Okay, if you remember your XOR function well, all right, so I call this one just let for explanation purpose. My D here, X, I just use the X and Y, easy for me to write, XY, and this is a XY bar. Let D be this one. All right, and by looking at these expressions here, you actually know that this is the same as my X, because this is an XOR expressions already. So this is an XOR. XOR is written as you OR, then you circle. So when you see this, means it's a XOR functions. Okay, I want to prove this one to you here is now, if I put a bar on this side and also bar on this side, Okay, I add bar on both sides, then you are going to find that D bar is the same as this one. Okay, plus Okay, so I apply De Morgan's theorem. What does De Morgan's theorem say? Okay, let's say you have A plus B and a bar across the whole expressions. De Morgan said that okay, you can break them into bar A, this plus or the or, you change it to become n. Okay, De Morgans also say that if now this is a n function and I want to convert this one here to become all functions, what I do is the long bar, I chop them to become two single individual bar, then this dot become all, terbalik. Alright, so this is De Morgan's theorem. Now I'm going to apply De Morgan's theorem into here, get rid of this one here. Alright, then you have is okay, not good enough. Okay, I need to apply one more time De Morgan's theorem on this. Then you find that I have x double bar plus the y bar. So this dot here, don't just write like this. Okay, it will be very confusing. So we use bracket. All right. So here x bar dot become plus double y bar. Okay. The double bar actually is the same as no bar. Can be written as in this form. Okay, same as no bar. So with this, okay, you find that okay, once I got this already, I can do my expansion x times with x bar. Like doing max now, x times with x bar. Next, x times with y, followed by these two times together. So I arrange that as xy. So xy bar. Next is y bar. Okay, we know that okay, anything okay, if they end it with their bar, like x bar, it is going to give me 0. This is going to give me 0. So this part here is the same as my xy plus x bar y bar. Look at it, same as this one, exactly the same as this one. So this is the d bar. All right. So this expressions here actually is the x no. Okay, this is x all Okay, x all. So once you put a bar across them, it then become x no. All right. So now d has been changed to this form. Okay. So this one here, now you look at it, this is same as like saying that okay, c. Okay, c d bar plus c bar d. Okay, so this whole thing here, we mentioned just now that is the d, right? So now I replace it with d. So from here, you can see very clearly that, okay, actually this is also an XOR function. C d bar plus C d bar, C bar d, okay, XOR function. Of course, okay, your d in this case here, d is the XOR with your y. So expand to this form. So you are going to find that the sum, okay, is actually 3 input XOR functions. Okay, so for this circuit design here, you find that I can use, okay, XOR gate. You may say that, okay, can I use a XOR gate with 3 input? Actually, there's no 3 input XOR gate. All the XOR gate are 2 input only. Therefore, we use 2 of them. 2 of them. And Sukahati, you can XOR these 2 first or XOR the C with the X. Okay, any combinations, 3 of them to get your sum output. And this part here, okay, you get your carry out output. So my full adder, just 1 unit by itself is this one. And full adder, actually you can buy it. Okay, it's available. So internally it looks like this one. All right, and these are design here. We call it as no small scale. Okay, it's a small scale integrated circuit. You can buy it as an IC. So, but this IC very simple 3 input, 2 output. And maybe in this IC here, you can have 2, okay, full adder in one shot. Then whereby you can join them to sort of, okay, add up, okay, more numbers. All right. Okay, now this binary full adder here only can add 1 bit at one time. All right. So when you want to add any bit more than 1 bit, therefore you need to sort of, okay, cascade them. Okay. So generally, okay, the equation for adding your binary number is given by this one. Okay. If you are adding, like I mentioned just now, the x and my y here, you have your x1, x0, y1, y0. Then the result comes out here is S0, S1, as well as S2. This S2 forms your carry out. All right. So in general, the result is n plus 1. You see, 2 bits. But result here, 3 bits. Okay. So the n here is 2, but result come out is 3 bits. Okay. So you find that, okay, I can, okay, of course, come up with a very complex design, okay. How many bits I want to add? Okay, I start to do my design. In that case here, your design can be very complex as the number of bits getting more increase. So in this case here, if I rebuild my this full adder, what I did just now, all right, the full adder with the inputs here. So you find that you can connect them in this way. All right. So these full adders here, the carry out from the LSB bit, this is my LSB bit, okay, becomes the input of the next bit, higher order. So you can add 2 bits, you expand, 4 bit, 5 bit, 6 bit, and so on. All right, you can connect them this way in order. And these are connections here, you call it as a parallel binary adder with ripple. Now, why they call it parallel? Because these are input, the X and Y inputs, okay? X and Y input, you can put in at the same time. So we put in parallelly at the same time, okay? So parallelly. But for me to get this carry in here, I won't know. Like I mentioned just now, I try to add 1 0 with 1 1. I know my carry first one is a 0. So sorry, I think it's 1 1, right? Sorry. Just now the example that I use is a 0 1. All right. So I was trying to add, let's say this one. Straight away, first bit I know is a 0. So I add up. I know it's a 0. So I won't be able to tell you what is the carry for this bit until I finish, okay, adding this part. Then I say, oh, output here is a 1 now. So this one will come in here. All right, then I add up some more. I got a 0 for this one. C2 again is a 1. So C2, let's say it's continue to here. Then I tell you, oh, C2 now is a 1. All right, so they add up this way. So all the carry in input except the LSB need to wait for the earlier additions to be done. Then only they will know what is the signal that coming in here. All right. So if this a full adder here, just take easy figure. This a full adder here require, let's say, 10 micros or nanoseconds, okay, to finish the task. I must add up, okay, takes me 10 nanoseconds to give me one result. So This one, the result can only be correct after the addition here another nanosecond. So I will be getting the correct result for this one here after 20 nanosecond. This one here is after 10 nanosecond. So let's say I have only 4 bits. So after 30 nanoseconds, okay, correct result come out. After 40 nanoseconds, all result comes out. So in this case here, in the middle of this parts here before the 40 nanoseconds, I may find that, okay, my S, okay, and my the C outputs here may vary, change. Okay, may suddenly, okay, change from 1 to 0 or 0 to 1, things like that. Because once the new data comes in here, the result, it will affect the result here as well as here. So therefore, if this is the case here, we say it produce some ripple, unstable signal. Okay, so the result can only be stabilized after 40 nanosecond in this example here. So easier to design, but it takes a little bit more time to be stabilized lah. All right. So of course, okay, if you want to go for, let's say, 16 bits of no additions here, then you may find that this one here, I must plan my timing. Let's say you are doing VHDL, okay, you must allocate enough time for it to respond. So I only want to see the signal, let's say, after 160 nanoseconds later. All right. So you add in the timing after a certain number of times. Okay, so you can do it this way and make your design simple, but with a little bit of ripple that you're going to see. So this is where all my explanation just now. Okay, all my explanations just now. So you are going to get a ripple, unstable signal. All right, this is our design. Okay, now we try to look at binary subtractor. How am I going to subtract, okay, a binary number? Okay, and I also hope that, okay, you all still remember your two's complement. So before we look at the two's complement first, we look at the truth table of a binary full adder. Full adder means that maybe just now I lend my number, okay, to other people. So I have to consider those things that I lend it to other people. So B here stands for borrow. Okay, and the previous bit borrow anything from me or not, or I lend out anything or not. Okay, so this one, oh, I didn't, okay, lend anything out. They never borrow from me. Yes, they borrow from me. Borrow from me, borrow from me, borrow from me. All right, so how do we get this outputs here? So the D here stands for difference because it's a subtractor. All right, difference. This is the borrow out. Now I have X, I have Y. My borrow is here. So purposely do it this way, not enough need to borrow. Of course, I start off the time, okay, clear, no borrow. My X is a 0, my Y is a 1. Okay, and what I'm doing here is my X minus my Y, X minus Y. Then, do I have enough, okay, to minus this 1 or not? If this is 1, this is 0, easy. Okay, do I have enough, okay, to minus this 1 or not? Answer is no. Then what I need to do? I go and borrow from this one. Okay, borrow from here. Okay, I borrow the time. So result is like that. You always ask, okay, 0 minus 1. Is there a difference? Okay, is there a difference? If your answer, yes. 1, no. Is there a difference? Do you borrow anything? So you borrow the time, this one becomes a 0. Originally is a 1. Now you lend it to other people, so becomes 0. 0 minus 0. All right. But just now because, okay, you borrow from somewhere, ma. All right. So this 0 minus 0 is a 0. And now because, okay, you borrow it, you lend it to other people, okay, you borrow out, then you find that, okay, you have actually just now here as a 1 here. You lend to other people, so borrow out. You borrow out. All right. So with this, okay, then wow, maybe a bit confused, y'all. Okay, forget about this one first. Okay, we look at this. So do it this way. This one minus this one minus this one. Okay, clear. Everything's 0. This one minus this one is a 0. Minus this one further. Any difference? Yes. Do you need to borrow to minus this one? Answer also yes. I repeat. This one minus already is a 0. So when you minus this one, ask yourself, is there a difference that you're going to get for the output? Answer yes. So you put a 1. Do you need to borrow to minus this one? Answer also yes. So you put a 1. Okay. So this one minus this one. This is what I'm saying. This one minus this one. Okay. This one minus this one. For time being, this one minus this one. Do you need to, your answer here, is there a difference? Yes. Okay. Do you borrow anything to minus this? Answer also yes. Okay. Continue. Minus this 0. Yes. Because, okay, 1 minus 0 is a 1. This one, just now I borrow. So I remain the borrow here. Okay. Proceed. This one minus this one, as earlier, is 1, 1. So now this 1, 1 minus this one. This one minus this one give you a 0. Do you borrow anything just now? Yes. This one, continue with this. Okay. This one minus everything, no problems. I think no problems. This one minus a 1 because this is 0, everything is 0. This one minus this one is a 0. 0 minus 0, still a 0. 1 minus 1 give you a 0. 0 minus 1, any difference? Yes. Do you need to borrow to minus this one? Answer also yes. So you get a 1, 1 here. Okay, so I hope it is clear for this truth table. So when come to here, now just now because, okay, I minus this one, I got a 1 here. I did borrow from something, somewhere, so I got a 1 here. So if I only consider a single bit, so you are going to find that, okay, you got a 1, 1. This 1 here is you borrow from elsewhere. The bit, okay, higher significant, okay, more significant than you. So you borrow it. So okay to all. So based on this, okay, let's say I want to design this circuit. Start off with using Kano map. Okay, start off with using Kano map. Then you find that I fill in, okay, I prepare 2 Kano map of 3 input variables. One is the borrow, the other one is the difference. And I fill in accordingly, and this is the result that I obtained. Wow, similar compared to my sum. Okay, for this one here. So I don't think I need to explain this part anymore. So you find that, okay, if you see your this part here alternate like that, XOR expressions. Which one you want to XOR first? Suka hati. Alright, suka hati, up to you. And this one here, when I fill in, okay, this is the expression that I'm getting. Okay, so I go and write out 1 loop, 2nd loop, and 3rd loop, 1 by 1. And with this, okay, of course, you find that I am going to use a multiplexer for this design, not shown, okay. So you construct your binary full subtractor using, okay, 2 XOR gates. Okay, and here, this one here is 1n, 2n, 3n plus 1 OR to build your borrow out. And in this case here, you find that this design here very troublesome. Can I do something like, if I want to have more bits, okay, to minus, can I combine it like what I'm not doing for the full adder? Answer actually yes. So let's say I already built up my binary full subtractor already. So exactly the same as just now. So this borrow, you bring it to here. Okay, borrow, you bring to here. First borrow, because it's clear, you never borrow anything, so we put in a 0. All right, so again, okay, you can have all your input x and y you put in at the same time. So parallel in, all go in at the same time, parallel in. But the outputs here can only be accurate after certain delay, depending on every one of this one here, how much is the time that they require to respond. Like the example just now, if I take 10 of them, for the case of 4 bits, 1, 2, 3, 4, I only will see my correct result, okay, after 40 nanoseconds. Because in the middle, okay, signal may be changing. Then you are going to see ripple. Therefore, these are circuits here, we call it as parallel with the ripple, okay? It's a parallel binary subtractor, but you are going to see ripple. But sometimes, okay, the labeling here, they may skip the word ripple. Consider as understood. All right, it's a parallel binary subtractor. You will only get the accurate result after some delay. All right, the delay here depends on how many bits that you are going to subtract. Okay, and the reaction time for the 1 bit of the selector. These are subtractor. All right, so next. Now, we also remember 2's complement. Now, any idea, okay, what is the 2's complement that we study in the year 1? So let's say if I were to tell you, take a very easy figure. I want to take 7 minus 5. This is in decimal. Answer I know is a 2. Okay, 7. I know it is given as a, let's go for 4 bit. So 0, 1, 1, 1. Okay, 5 is a 0, 1, 0, 1. 5. So if I minus, I can do it this way. 1 minus 1 give me 0. 1 minus 0 is a 1. 1 minus 1 is a 0. So this one is a 0. Yes, I got the 2. Okay, I got 2 minus. Okay, besides doing it this way, I can use the 2's complement. Then I do addition instead of subtractions. What does it mean by 2's complements here? The 1 minus. Okay, this is minus 5. So with this minus 5 here, of course, okay, 5, I convert it first to 0, 1, 0, 1, this one. All right, then I find the complements of it. Okay, so the bar 5. Okay, complements of it. So you find that when I complement this one, I terbalik all this, complement all this. 0 change to 1, 1 change to 0. Okay, correct. Okay, so this is what we call 1's complement. Okay, 1's complement. Okay, 1's complement. After doing 1's complement, I add 1 to it. Then this one here forms the 2's complements. 2's complement. So add 1 to it, you get a 1, 0, 1, 1. Okay, this 1, 0, 1, 1. Now, I take this 1, 0, 1, 1, the 7 is a 0, 1, 1, 1. I take the 2's complements of my 5, which is 1011. I add them together, sum them together. Then you are going to find that addition. 1 plus 1 give me a 0 with a carry in. 1 plus 1, 3 ones are, so I got a 1 carry in. 1 plus 1, 0 carry in. 0 carry in. So this one here you discard because we are talking about 4 bits. Here got 5-bit array. So whatever here extra, you just forget about it. 4 bits only. So you find that the result here is also same as this one, 2. Okay? So 2's complements here normally used in the computer for this type of subtractions. Okay? You subtract. Whatever number, you find it first complement plus 1. Then that is the 2's complement. With the 2's complement, if you want to subtract or minus, okay, whatever number here, find their 2's complement, then you can sum them together. So with this, okay, now I don't need to build my subtractor. I make use of my full adder. I go and now see the word here. I use full adder. And you find that the result that coming out here actually is a subtractor. So how do I do it? X minus Y. Okay, so X don't do anything. Y, I make it go through an inverter. All the Y, make it go through an inverter. By making it, okay, go through the inverter here, it's the same that saying that first complement. You're trying to generate the first complements of your Y. How to get second complement? The carry in here. Carry in now, you make it equal to 1. So you add 1 to all these number here. So that means your Y now, okay, converted, okay, to the 2's complements already. Okay, so maybe I write here. Y is first complemented first. Complement in this case here means you not it. Okay, then plus 1 to it to form 2's complement. Okay, so these parts here, we are changing it to form 2's complements. So with that, okay, I no need to build my subtractor. I can make use of the full adder because full adder is very common. All right, and computer is using this concept, okay, to do the subtractions. All right, of course, in this case here, I can also only get the correct result after some delay, depending on the full adder's delay here, and the delay in this case here propagate. All right, depends on the number of bits that you are going to have. So be careful now. The result here is no more sum, but it's the difference. Although the label here is a sum, but you should know that this one now is a difference, and this is the borrow out. Okay, borrow out. But we are using, okay, the full adder to build a, subtractor. All right, so I hope this is clear to all of you. Now, this part here tells you, okay, when I XOR it with 1, so if, okay, I want to generate a design, okay, in this case here, just with one control input. If I put some control input, it functions like a full adder. If I change the control input, then it functions like a subtractor. So what I can do now here is I try to play around with this part. Let's say the Y now, I XOR it with 1. So when you XOR it with 1 here, then you are going to find that, okay, you XOR Y let's say y bar, then 1, no? Plus with y, you x bar 1. Of course, okay, this is the same as y, right? Y bar. And this one here, because of this parts here, bar 1 is going to give you a 0. So if I make use of an XOR gate, one of the input, okay, I connect it to a 1. Then you are going to find that I will be able to get my y bar. Okay, I will be able to get this. Right? How come I duplicate this one? So I should delete this page. Okay, so you find that, okay, I changed the NOT gate here into XOR gate. Okay, I make this one here connect to a 1. Let's say I connect it to 1 first. Okay, then the output here will be a bar. But if I put here become a 0, let's say the input here, I put it become 0, then of course, okay, you are going to get like this. 0, let's say I put it to 0, then you get this one, which in this case give you the y. Give you a y. Y means that I didn't complement it, isn't it? So this part now, forms like the control input. Okay, if you want to do addition, okay, if you want to do addition, you connect a 0 to it. Okay, here you put a 0. Then this circuit here function as an addition adder. Okay, it's an adder. If you want to do subtraction x minus y, then you put a 1 to here. 1 here, with this 1 here, well, the output here will give you the subtractions output, the borrow and the difference. So our design, okay, always, okay, something like 2 in 1. All right, we just don't want to do it as a single function. So more flexible by adding additional control. Okay, so if 1 or subtractor, if it's a 0, it forms as a adder. By changing this NOT gates here into XOR gate, you can achieve these functions that you want. All right. Okay, that complete for these adder subtractor parts. I don't think I can finish the comparator. Yep. Never mind. We continue on Monday. Okay. Any questions? Let me stop first. Any questions? Adin, okay? Can I understand? So always remember when you are doing designing, okay, you don't want to make your design here too complex. Okay, too complex, okay, you design a simple one, you cascade down. But take care of the propagation delay. You cannot get the result, okay, especially, okay, when you are doing simulations. So why the result, okay, keep on changing here, or maybe because of a ripple. All right, so with this, okay, you can do some tutorial questions. There are quite a number of multiplexer tutorial questions. So start trying and start writing your this VHDL code. All right, next week we are going to do online. Wow, yesterday, okay, 29,000 already. Going to hit 30,000, okay, very soon. Okay, so next week we do online. So online means that, okay, for next week's lab is like that. You all do. I am not going to teach you anything unless you ask me questions. No question, I just do my own work. Understand? All right. Okay, so if no questions here, next week, Monday, okay. Yeah, Monday we will start at 10. So 3 hours continuously. So if it's too tired, okay, for lecture, we can spare 1 hour for tutorial. So please do your tutorial on multiplexer first. So 3 hours lecture very heavy, okay? So 1 hour for tutorial. on these 5 input variables. I remember, okay, there's one part on 5 input variables. And also there is some questions on the AND gate and OR gate. So recall how to design making use of AND gate, NOR gate, NAND gate, these are of features. So the first page and the second page. Up to your tutorial on multiplexer. Okay to all, please do your homework. I think you all are good boy. Okay, we'll do all this homework. All right, we are going to stop here. So see you again. See you all again on Monday. Okay, 10 a.m. Okay, bye bye. Thank you for paying attention. Bye bye.